Right, let's see everybody. The second part of GOC is about understanding reaction intermediates. So we have mainly 6 reaction intermediates which we observe in chemical reactions, in organic reactions. That includes carbocation, carbanion, free radical, carbene, benzene, and nitrene. Okay. So during the chemical reactions, in organic reactions specifically, you might come across these intermediates in general. Now I'll explain you what are intermediates as well. Okay. First, let us understand what is bond fission. Okay. To go through more into details of these intermediates, we need to understand what is bond fission. Now, how you break a bond between two atoms, that can be done in two different ways: homolytic fission or heterolytic fission. Okay, we use the terminology homolytic fission. We use the term homolytic fission if the electronegative difference between the elements is negligible or zero. As a part of example, you can write along with me, everybody. For example, if you have uh, Cl and Cl molecule like this, okay, Cl and Cl bond. Now this, if you provide heat, I mean light or heat, what happens is this bond will break into equal pieces as in it's a pair of electron, and it will convert into two chloride ions. Now this chloride ions, I mean at chloride radicals is what we call it as free radical. So in short, a homolytic fission is about generating those free radicals. On the other hand, if it is heterolytic fission, which means there is an unequal fission of covalent bonds. When do we observe that? If certainly there is some electronegative difference observed. For example, if you have PHCH2 connected with bromine like this, and this, if at all you're adding in aqueous solution, chances are this bond will break, but it will take the electrons only towards bromine, thus giving us PHCH2 plus, which we call it as carbocation, and Br minus. So you can see we can get this as carbocation here. Similarly, if you have CH3 MgBr, Mg and Br, specifically if you have a carbon atom connected to a metal, carbon's electronegativity is always more, which means if this is going to be breaking, okay, yeah, check. If this is to be breaking the bond, then electrons will more likely be shifting towards carbon rather than magnesium. So which means you will get something like CH3 minus and MgBr plus. And this CH3 minus is what we call it as carb and ion. Carb and ion. Okay. So intermediates are of these two types, carbocations and carbanions. So you can see, so far we came across 3 intermediates here. So one is free radical, carbocation, and carbanion. So that means every uh, intermediate formation is either a part of homolytic fission or heterolytic fission. Got it? In generally, how do we define the intermediate? See, intermediates are those species which are formed during the reaction between the two transition states. Let me explain you. more in terms of how the molecular bond breaking takes place. Suppose if there is a reactant here and the potential energy of the reactant, this R means reactant. This is the potential energy of the reactant. Over the course of reaction, the reactant is, let's say, changing its potential energy like this. Okay, which means when this potential energy is almost similar to this or less than that or slightly greater than that, that is when we say the product has formed. So from the reactant, it has gone through product formation. Okay, just a second. See, when the potential energy of a reactant is raising, which means there is a bond breaking taking place. And instead of directly coming to the product, if it is taking a pit stop like this, then the place where it is lowering its potential energy from a very high potential energy. So you can see this highest potential energy state is called as transition state. And this is also a transition state. Now remember, an intermediate stage is always formed between the two transition states. That's what I have defined it. Clear? So I hope all of you understood the definition. What exactly is intermediate? Usually, an intermediate's energy of an intermediate is always greater than either the reactant energy or the product's energy. And these kind of reactions where you have intermediate formation before a product forming are called as complex reactions. Complex reactions. Complex reactions are usually multi-step reactions. Multi-step reactions, which means you can see here the step one, being reactant trying to convert itself into an intermediate. The step two is reactant trying to follow up towards the product formation. So there are two steps that are happening in this reaction. Clear, everybody? This is what we call it as intermediate. And there is one more important term we should remember is, you can see this much amount of extra energy a reactant has to gain so that it can reach this maximum point or maximum transition state. So that particular point is what we call it as activation energy. So minimum energy required for reactant to reach the highest energy transition state. Highest energy transition state. That is what we call it as activation energy. Okay. I suppose this point is clear to everyone. Next. Transition state is the highest energy state of the reactant or the intermediates. Okay. And another term you might be also interested in knowing is that the molecular geometry, the molecular geometry at transition state is called activated complex. This is another term you will come across, so remember this term as well. Activated complex. These are few basic definitions you should know. And these definitions will be very helpful even going in physical chemistry when we discuss kinetics and all. Now, let's go through carbocations. But before that, I want you to make sure everybody is clear with these terms and you have made a note of this terminology. What is activated complex, activation energy, transition state, and what is intermediate? Shall we go ahead? Everybody, please check. Right. Now let's understand what are carbocations. Carbocations, another terminology is carbonium ion or carbanium ion. Structurally, it would have a positive charge on an empty orbital, and in three dimension, this is how we show it, that there is an empty orbital which carries a positive charge, and there is one bond here, and there is one bond which is going inside and one bond which is coming outside the plane. So that makes this particular group, all three bonds are on one particular plane. Okay. And this lobe is above the plane and this lobe is below the plane. So that makes this carbon an sp2 hybridized and planar geometry. So when the carbocation is sp2 hybridized, it would be planar, right? And this is how it looks like. Suppose if it is sp hybridized, which means there is double bond and a single bond. In that case, it will appear more linear like this, double bond with an empty orbital with positive charge. So here the hybridization on carbon is sp and linear. So structurally, this is what you will notice about the carbocation. Next, if we are talking about a carbocation with three phenyl groups on it, three benzene groups on it, this would usually exist in a propeller shape instead of planar structure. So if this group, they are all in planar molecule, planar surface, then they will have more repulsions between their electronic clouds. To avoid that cloud, they will start slowly rotating around so that see this carbon, this carbon, this carbon, and this carbon, they all are on one plane. But thereafter, this carbon will try to keep the next two bonds of it such that they are less repulsive to this, they are less repulsive to this. And that gains a propeller type of shape here. So this is only one situation where the molecular form shows a propeller shape. Otherwise, in general, carbocation is planar structure. How do we generate the carbocation?
So can you scroll up?
Carbo. Yes, beta.
1 second, please.
Yeah.
Answer.
Right. The next point we need to emphasize about carbocation is how do we generate it? Carbocations are usually observed from alkyl halides. Okay, alkyl halides like RCl. RCl. When you make them to react with something like AlCl3, AlCl3 is used here as a Lewis acid. In that case, it will become R plus, okay, and here we will have this as AlCl4 minus. Okay, it's nothing there here. So it is R plus and AlCl4 minus. Okay. La here represents Lewis acid. And is it only one Lewis acid? No, other Lewis acids can also do the same job. So we can have BF3, BCl3, correct? we might have SOCl2, POCl3, PF5. All of these can act like Lewis acids. What they can do, they can take this chlorine away and generate this alkyl group into R plus. That's how carbocation is formed. Okay. Now see the typical mechanism if at all I have to show it. See, chlorine has three lone pairs on it, and AlCl3 on the other hand has an empty orbital on it. You know that that's the definition of a Lewis acid, right? It must have an empty orbital. So lone pair present on chlorine will try to support it like a base, Lewis base. And while doing that, while chlorine is trying to attract itself to aluminium, its bond with the alkyl group becomes weaker. So now, in a way, you can see we are reaching out to this complex formation, okay, like this. So this is the molecular situation in a complex formation, correct? And this particular complex formation is what we call it as the energy of this complex formation is what we call it as transition state. So this is the transition state. So from the transition state, it will convert into R plus AlCl4 minus. And this R plus is what we call it as intermediate. So I guess the terms are clear, everybody. By the way, this is the symbol that is used for showcasing transition state. Next, we can generate carbocations even from alcohols. Same logic. If you have OH and alcohol, in the presence of Lewis acid like H plus, it will take that H plus onto it, converts into OH2 plus. OH2 plus remains less stable. It will release out easily from alkyl part and convert itself into R plus and H2O. This is another way of generating carbocations. One more way of generating carbocations is from alkenes or alkynes. Suppose if you have an alkene like this, propene, then when you react with an alkyl halide like this, sorry, uh, hydrohalogen here, HX, here X could be fluorine, chlorine, bromine, or iodine. In that case, the pi bond as a nucleophile will take the H plus, which is an electrophile. So H plus will get added onto this position and positive charge will form on this position. In the last class, we studied about electromeric effect. When H plus is nearby the propene, automatically it will start showing delta plus and delta minus here, so as to attract the hydrogen which is delta positive and X being delta minus. That's how these two will start attracting and eventually this carbon will get complete positive charge. Correct? Now, the positive and negative charge could be happening on the either direction. So we can expect that we can get hydrogen and halogen here with delta positive and delta negative. And this might get delta negative and this might get delta positive, and this delta negative can attract this H plus. Both can happen. So like this, we can have H getting added here and plus getting formed. Now, last class, we also discussed about hyperconjugation. Now you can see based on the hyperconjugation, which is more stable intermediate here. So you can see there is intermediate 1 and intermediate 2 forming. So if you compare the stability wise, you can clearly notice that intermediate 1 is more stable than intermediate 2. Why? At intermediate 1, we have 6 alpha hydrogens. Intermediate 2 has only 2 alpha hydrogens. So more the alpha hydrogens, more is the hyperconjugation. And that way, we can also get carbocations from alkenes. Same goes with alkynes also. So in case if you have a triple bond here, and then you are adding something like HX here, so we can get double bond with H getting added and positive charge coming here. This is the way we can generate alkenes from uh, carbocations from alkenes and alkynes. Primary amines, for example, NH2. This is primary amine. Primary amine, when you react with HNO2, it generates a very peculiar compound like this, N2 plus, and this is called diazonium, diazonium ion, diazonium ion. And diazonium ion is very unstable form, so it will immediately break into this part where nitrogen gas is coming out, and then we will get a carbocation here like this. I'll do one thing, I'll add one more methyl group just to showcase that this is propane form like this. So we'll get this propyl carbocation, clear, plus N2 gas. N2 will evaporate as N2 gas, giving this intermediate, which is a carbocation. So I guess all of you understood how the carbocation is formed. Mainly in organic reactions, these are four major parts in which we can see carbocation formation is observed. All good? Shall we go ahead?
So in the first one, the alpha hydrogen should be 5 or 6.
Where beta? Here.
Yeah.
Left side I have 3, right side I have 3, including this hydrogen.
Okay.
Okay. Next, how do we assess the stability of carbocations? Check. The factors which affect the stability of carbocation includes resonance, hyperconjugation, aromaticity, inductive effect, and a new term called dancing resonance or sigma resonance. Dancing resonance is also termed as sigma resonance. First, check this example. If I have to compare the stability of these four groups, okay, so I'll give you the idea that out of the stability, the last one has the highest stability. That is because of two effects. One, plus psi effect. There is no donating groups on CH3 plus. Here there is one donating group, so one plus psi effect. Here there are two methyl groups, so more plus psi effect. Here there are three methyl groups, that means even more plus psi effect. While hyperconjugation, if you notice, there is no hyperconjugation here. There is alpha hydrogens which are 3 here. There are alpha hydrogens which are 6 here. There are alpha hydrogens which are 9 here. And you know that if plus psi increases or hyperconjugation increases, it will increase the stability, increase the stability of carbocation. Thus, you will see this carbocation is more stable than this one, and this one. Here, the carbocation has three carbons connected to it, so that's why it is called tertiary carbocation, secondary carbocation, 1-degree carbocation, and methyl carbocation. So, this is the standard stability of carbocations. I guess this part is clear, everyone. See the second case. You have tertiary carbocation, benzyl carbocation, and allyl carbocation. If the first carbon present on benzene, right, has a positive charge, that is called benzyl carbocation. If the carbon present on an allyl carbon, right, that is called as allyl carbocation. So if you are to compare 3-degree carbocation, benzyl carbocation, and allyl carbocation, Then notice what are all the effects you will see. The first effect being, see the effects if you compare. Here we have high amount of plus I. Here benzyl usually shows minus I. Allyl, there is hardly anything because this carbon and this carbon has mostly same electronegativity. So it will not contribute much to the carbocation. Second, if it comes to resonance effect, you can see there is no resonance here. But in benzyl, you can see the pi bond can move here so that the positive charge can keep moving across this benzene ring. So there is a sufficient resonance that is happening. Allyl also has a resonance happening. Okay. And now notice hyperconjugation. Now you have 9 alpha hydrogens. Here we have 0. Here also we have 0 alpha hydrogens which will participate in hyperconjugation are 0. So plus psi is a stabilizing effect. Hyperconjugation is a stabilizing effect. Here minus I is slightly destabilizing, but resonance is highly stabilizing. Here also resonance is highly stabilizing. Keeping this into picture, we usually say that resonance is always dominant effect than hyperconjugation as well as inductive effect. But in this case, specifically in this case, these two has stability very close to each other. So much so that 3 degree is slightly more stable than benzyl carbocation, which is mostly more stable than allyl carbocation. Okay, so here we can say in 3 degree carbocation, 9, 9 alpha hydrogens will dominate over resonance effect in benzyl carbocation, right? That's why this order is slightly different. We expect that benzyl, allyl and 3 degree should be the correct order, but now what you will notice, 3 degree, benzyl and allyl, that is the correct order. Everybody, the first two cases are clear, beta? Right. So this is an exceptional case where a plus psi and hyperconjugation dominates over resonance. See the third case now. Third case where nitrogen, oxygen and fluorine are directly linked to carbocation. In such case, you can see a resonance that is taking place. Lone pair sigma plus, that is a resonance. Lone pair sigma plus, lone pair sigma plus. Okay. In case if at all I have to write the resonating structures for the same, this is how it look like. R2N double bond CH2 with a plus charge on it. RO double bond CH2 with a plus charge on oxygen. F double bond CH2 and a plus charge on fluorine. These are the resonating structures. Now, if you compare nitrogen, oxygen, fluorine, who can handle positive charge much more easier way? Nitrogen, because nitrogen's electronegativity is less than oxygen and fluorine. Therefore, stability wise, if you compare, this carbocation is more stable than this one. Okay. Hence, if I give the numbering, I can directly write this here like this. This is the stability order. It is based on the electronegativity of the atom which carries the positive charge. Next. Now, just to close this case, you notice that initially when carbon has positive charge, its octet is incomplete. Now, after nitrogen giving the electrons and making a pi bond, now you see the number of electrons on carbon are 8 and nitrogen is also 8, which means octet has completed. And these kind of cases or these kind of resonating structures where octet is getting completed on a carbocation. Those are called OCC, octet completed carbocations. Octet completed carbocations are priority wise most stable forms of carbocations. Okay, next, check out this case. Stability due to hyperconjugation as the main effect. You can clearly notice that alpha hydrogens here are 0, 3, 2, 1, and 0. And if I compare the plus I, there is nothing here. 1 plus I, slightly better. This is even better. And this is much, much better plus I effect. And hyperconjugation is a very dominant factor. So first priority is always to hyperconjugation. So therefore this one. So which means if we compare the stability A, B, C, D, E, then stability wise you notice that B is more stable than C, then D, then E, and last comes A. Everybody clear with the fourth case? See the next one. There is a carbocation already present. One methyl is pushing here, one methyl is pushing from here, one methyl from here, nothing. So if you compare the stability wise, this methyl is much closer towards CH2. That means its plus I is more effective than the plus I here and the plus I here. Okay. And other than that, if you compare the stability alpha hydrogen wise, you notice that this is A has, three alpha hydrogens here. Here on the meta position, this is called ortho position, this is called meta position. On meta position, CH3 will not operate any hyperconjugation. Hence, here we can take it as 0. Sorry, first case we have uh, 3 here due to this CH3 group. But here CH3 is inactive. Here again 3, here we have 0. So alpha hydrogens are sufficient here. Okay. And if we compare the stability, in this case, if you compare the stability, so clearly we can see B has more stability because its hyperconjugation is not affecting the carbocation. Sorry, not B, A. A has more stability because of the positive charge here. This methyl is going to support that positive charge on this case. Next comes C, next comes B, next comes D. This is the stability order. Next, if you have trimethyl carbocation and trimethyl with a deuterium carbocation, between these two, if you compare the order, now you can see this one has more stability, tertiary carbocation. So bond energy will be C and D bond is greater than C and H bond. So here carbon and hydrogen bond, carbon and deuterium bond is stronger than alpha carbon and hydrogen. So which means if you compare the strength of hyperconjugation, strength of hyperconjugation, you will notice that in the first case, suppose this is 1, this is 1, and this is 2. So in the first case, if you notice that we have only hydrogens connected. So hydrogens will definitely give a better hyperconjugation than deuterium. So that's why strength of hyperconjugation will be better for 1 than 2. And that's the reason this is the stability order. Okay. Now please check the seventh case. So we have a carbocation and then we have OCH3 with a carbocation. OCH3 is methoxy group connected at either ortho, meta or para positions. What is the effect OCH3 is bringing to benzene now? See, when it is at ortho position, you will notice that resonance energy is observed, which means the lone pair will try to push the electrons towards itself. I'll show you the structure for once. Check it out, everybody, how resonance is helping. If CH2 plus is there here, okay, let me just copy 3 4 images first. Now notice, if OCH3 is there at ortho position here like this, OCH3, and pi bonds are present this way. So you can see the lone pair will push electrons here, and thereafter the pi bonds will move here. So that means we get this as OCH3 plus positive charge, sorry, negative charge will come here. Okay, pi bond and pi bond will be present. Next, that negative charge will keep moving across this benzene ring like this, double bond OCH3 plus. Again, this will try to push here, removing this pi bond. So we'll get minus charge here, double bond here, double bond here, and double bond OCH3 plus. Likewise, the last case also, you can notice that this positive and negative charge can make a double bond formation here. So in a way, we are making this uh, like this, CH3 plus. So what we notice that we made a carbocation and a negative anion here, both to make it into a pi bond formation. Okay. So I guess you understood, if it is at an ortho position, it is, very much helping the carbocation to get more stabilized. That's why resonance energy should be always operable only at ortho position and para position. Meta position, never apply any resonance. That is not contributing. Next, OCH3 has a minus I effect, and you know that minus I effect keep decreasing as it start growing the distance. So you can see para is at a farther distance, so that's why it would have only resonance energy and no inductive effect. And that makes, because electrons are totally donating both by resonance effect as well, sorry, minus effect is withdrawing, but resonance energy is uh, donating. So overall electron donating group is observed at ortho position. Meta, you have only minus effect, so it is electron withdrawing group, and para position, it is again electron donating group. So it is electron donating. So you can see, this is electron donating, this is electron donating. So both will try to donate the electrons on that benzene ring. Hence, more the donating nature, more is the stability of carbocation. While on meta position, if you notice, it is actually withdrawing. Now you might wonder, sir, यहाँ पर resonance भी हो रहा है, inductive हो रहा है, which one should be given priority? You know that as much as resonance is concerned, that is always very, very high priority than minus I. Same logic on para also. Resonance energy is almost dominant effect compared to minus I. That's why if you compare ortho and para, they are electron donating. Meta is electron withdrawing. Now between ortho and para, which one is more amount of donating? It is para. Why? At ortho position, resonance is same. Ortho and para position, the resonance is same. But the inductive effect, minus I is more on minus I, ortho position and less on para position. So withdrawing nature is less on para position, hence it is more stable. So therefore, if you compare the stability here, then what you will notice that para is more stable than ortho, then H, then M. H means only benzyl carbocation, only this one is H. No groups are present means H. And para, ortho, hydrogen, and beta. That should be the order of carbocation stability. If anybody has a problem in understanding, please do ask right away. Okay. Right. Right. Let me explain this order. The lone pair present on this oxygen will try to push the electron. So that's how its octet gets completed. And that's the first priority of stability of carbocations. Next one, this is called CPM carbocation. There are three of them. More the CPM forms, more is the stability. That means here this carbon is connected to one more CPM. Here it is connected to one more cyclopropyl. So more the number of cyclopropyls we have, more is the ring opening taking place. More ring opening means more stability. So first 3, 2, 1. Sorry. Ah, these are all the number of methyl groups which can be number of cyclopropyl groups that can be stabilizing. Thereafter, you see this one, tropylium and cyclopropenyl. Both of them are aromatic compounds. The positive charge is a part of an aromatic ring. That's why aromaticity is the next priority. Next, normal resonance, that is 3 degree, 2 degree is a normal resonance effect. And usually PHCH2 is also a resonance, but just earlier we learned that between 3 degree and benzyl, 3 degrees slightly more stable than benzyl. Then comes allyl, then 2 degree, then 1 degree, then methyl. Now notice after methyl. After methyl, if the positive charge will start getting a double bond, it will become highly unstable because now the carbon is sp2 hybridized. And you know that more the percentage S character is, more the percentage S character is, less will be the stability of carbocations. Okay, just a second. Right. So you can notice that here we can see this is called vinyl carbocation, and vinyl carbocation is highly unstable. Then we have phenyl carbocation, which is also highly unstable. Then we have acetylene carbocation, acetylene carbocation. Then we have bridged carbocation, and last we have anti-aromatic carbocation. So out of all the carbocations, the least stable form is anti-aromatic form. Okay. So this sequence is important as well, everyone. So that is methyl, vinyl, phenyl, acetylene, bridged, and anti-aromatic. So this is the total order of carbocation stability. Good, everyone. Now let's notice what is the fate of carbocation means. Fate means what would happen to the carbocation. See, any intermediate for that matter, their lifetime is not more than any milliseconds. Okay, they are hardly going to be sustaining or stable for more than some milliseconds. They will immediately try to convert into some product formation, which means whatever the carbocations which we are making it, sooner or later they will convert into a product. So, while converting into a product, how will they do that? For example, they can combine with a nucleophile and convert into a product. Like a carbocation is present, OH minus is a nucleophile. These two can combine to convert into ROH, which is neutral. Similarly, you can undergo elimination also. That means a positive charge is here, and then some alkoxide group is there. Instead of attacking on the carbon, it might take proton from the adjacent carbon, convert into a double bond plus ROH. This is also a reaction. This is called elimination reaction. Okay. Likewise, a carbocation can undergo a very important case study that is called rearrangement. Now, how does this rearrangement take place? Please notice. For instance, if you have a positive charge here, a positive charge here, which is at 2 degree position, correct? Now, carbon's 2 degree position. Now, what if the same positive charge erupts onto this position? Then this will become 3-degree carbocation. And you know that between 2-degree carbocation and 3-degree carbocation, in generally, which one is more preferable? You can see 3 degrees more preferred than 2 degree. Therefore, 3 degrees more stable carbocation. So if we compare between this 2 degree and 3 degree, the second one is being more stable carbocation. Now, this activity of making one rearrangement to the other rearrangement, this is called 1,2 hydride shift. This is called 1,2 hydride shift. How does it operate? Now, notice the structure. Basically, you have something like this. We have hydrogen being present here and carbon having an empty orbital present here. Now, if you compare hydrogen's body, it is spherical in surface like this. So, spherical surface can easily come and overlap on this particular pi bond. So, as it start overlapping, that means it will start showing this attraction towards this orbital. What you would notice is that the bond will start breaking into H minus, and that H minus will support here. And if between carbon and hydrogen, if hydrogen becomes H minus, this carbon will become carbon positive. So that's why you will get a positive charge here, hydride getting shifted here like this. So that's why we call it as a hydride shift. 1-2 position because it is position 1 and 2. So hydride is shifting from position 1 to position 2. That's why it is called 1-2 hydride shift. I guess this part is clear, everyone. What is hydride shift means? If I write the same thing in terms of number of alpha hydrogens, you can clearly make out that number of alpha hydrogens here are 4 initially, 3 here and 1 here. Now, number of alpha hydrogens in this case are how many? You can see 3, 3 and 2. So total 8. So definitely there is a good improvement in terms of alpha hydrogens. That's why this rearrangement is valid. Okay, everyone, please check. Right. Which all groups can shift like this? Is it only hydrogen? No, not necessary. It could be hydrogen. Any alkyl phenyl group can be rearranged. And more such rearrangements, more is the stability. More is the stability. Now notice here, when it comes to rearrangement of these cases, it is observed to attain more stable carbocation 1,2 shift. Yeah. One second. Yeah. You can clearly see that generally migrating aptitude, that means ability to migrate from one place to the other place, adjacent place, will be highest for hydrogen, then for phenyl with donating groups, then with only phenyl, or thereafter it is phenyl with electron withdrawing group, then normal 3 degree, 2 degree, 1 degree, and methyl. So this is how the migration usually takes place. Let me show you some cases here. For example, carbocation is here. Now this is a 1 degree carbocation and number of alpha hydrogens are 0. But nevertheless, here, if I compare the structure here, second, yeah. Now if you compare this case, now here the alpha hydrogens are 0 because adjacent carbon does not have any alpha hydrogen. But what I can say, isopropyl here can shift much more easily. So what we do, this isopropyl, we will shift onto this carbon And what do we get this as? CH3, C, C2H5 with positive charge here, and sorry, and this methyl group has shifted here like this, and CH2. Yeah. This way you will get the shift here. So what is this one? An alkyl shift. An alkyl shift can take place like this. And why only this has shifted? Why not ethyl and methyl? Because isopropyl has uh, more migrating aptitude. I guess all of you got that. Second one, between hydrogen, phenyl, and methyl, which has more migrating aptitude now. So that is phenyl, which can do. Similarly, if you have two methyls and one phenyl here, so still you can go for phenyl. Sorry. In the first case, hydrogen is there, first hydrate shift will take place. Second case, there is no hydrogen, so between two methyls and phenyl, phenyl will take care of it. Yeah. Next one. If you have a carbocation here, adjacent to that, we have a toluene group, we have nitrobenzene group, and phenyl group. You know that here this is electron donating species, sorry, electron withdrawing group. So it cannot stabilize. While here it is electron donating species. So electron withdrawing group, electron donating group. So because it is electron donating, that means this group can easily migrate here. So that's why you migrate this carbon here. So on doing that, we will get this as pH, and this one plus NO2. And that is connected to, this particular carbon is connected to CH2, to which, so here this is the shift that has taken place, and a positive charge will be present on this carbon position. Okay. The last thing about the carbocation is also expected to undergo ring expansion. And ring expansion usually take place, and ring expansion is also called as a rearrangement, by the way. Okay. So how does this take place? Suppose a positive charge is here, alpha hydrogens are 2. Now I can make it into a little bit better carbocation, like this, with getting a positive charge here. So now the alpha hydrogens here will be 4. Thereafter, once you get the carbocation here, right? Now, what would happen? Instead of this positive charge coming here, instead, you will notice a ring getting broken here. And from here, you will get delta negative charge, delta positive charge, and this delta negative charge is the one which you will connect. So that 5-membered ring will convert into a 6-membered ring with a methyl group, and positive charge will be somewhere here. That's it. Okay, sorry. Let me put the numbering also for the sake of it. Here we have positive. I'll show with the numbering here. 1, we have 2, 3, 4, 5, and 6. Yeah. So you can see this is 6, 5, 4, 3, 2, 1. This is how the ring expansion takes place. So this is the same thing I have written. So first carbocation will come at this point, and once the carbocation is there, it will undergo further rearrangement here. So you will get a positive charge at this position. You just count the number of alpha hydrogens. Here there are 4, and here there are 3, and here there are 7. So these are the number of alpha hydrogens. All good. Next one, I would suggest you to try it out once. Please check out. First, write the expansive product, and thereafter check out this question. If alpha hydrogens are 2, right, then what will happen? Let me show you how to make this ring expansion. So it's clearly defined that there is a 4-membered and 5-membered ring. So 4-member, because it has more strain, that will expand first. So what would I get here? So first from here, on this carbon, we will have a 5-membered ring formation like this. Okay. So once it is connecting from, let's say this is 1, 5, 4, 3, 2. On second position, we have a positive charge here, right? This is the positive charge which you will get. And that positive charge can be rearranged again on to the top of the carbon here like this. So this is done via 1,2 hydride shift. And again, you can see the ring expansion can take place, bond breaking can take place here. It will attached, right? So now you can see here this has 5-membered ring has become a 6-membered ring. And as it happens, you can get this into 5-membered ring. Correct. As you expand that, the positive charge will come at this position because this is where the positive charge will come. And that positive charge will be further rearranged here to get into this position. And once the positive charge come at this position here, right? So that is when this body will break here. I mean, the bond will break here and attach on this position. Thus, we can get, sorry, now this has also become 6-membered ring with a positive charge here. Okay. So this is how you can get various carbocation formations here, everybody. Please do check with all the intermediates. Okay. Check again. Positive charge which is present here. First it gets rearranged to this position. So alpha hydrogens are 4. And from there it reaches to this position. Alpha hydrogens are 6. And from there, if it goes to this position, alpha hydrogens are becoming 4. That means this is not possible. The rearrangement is always in the direction of progressively increasing stability. But here there is no progressive increase in stability. That's why you need to only stop at this point for final stability. Okay. Everybody, all good? Right. So this is the basis of carbocations that you need to know, everyone.